good time to in progress. All right. Maybe talk to your other instructors, like find out when you're having other midterms. I assume you'd like to avoid stacking everything in one day or whatever. Um, I don't think, I mean, my feeling about it is just is this. So we can always, I can just say, well, it's a non-issue because we'll do it by the end of the quarter. But then that's not very fun as a student. I wouldn't like that. We'd have to go on to the new material, which you also have to keep up with. And now all of a sudden I'm asking you, okay, remember the stuff we did? We have a test. Um, so I think it would be better if we can do as little as possible of new material while you still are responsible for the old material. There is no comprehensive final. So I mean, once you get through it and you've shown you mastered this first unit, we're good. Okay, so yeah, so you can be thinking about that, and let me get into it another hour. I did tentatively put up the first homework, which you are not going to be able to just blast through yet. But there might be like a breadth first problem on there, which you could do, or a uniform cost, which you could do. So I'm putting it up as trying to err in the way that gives you the most flexibility with your time. So if you want to kind of get on that right away and make some progress, be my guest. The other thing I will point out is that in in the top level of the Sakai, I have a zip archive. Again, this first unit's special. It's been part of this course like forever. So there's been a lot of test ones. And so there's like five or so old ones. They're not perfectly aligned with the way we teach the material here. So if you see like this topic, we did not cover this topic, don't worry. You probably didn't miss it. You can ask me, but you probably didn't miss anything. It's probably just an old test one topic that isn't covered anymore in test one. Um, but most of it is good. It's got a lot of questions of the type that are on the actual test one. So, and we will have time. Again, just to remind you, so for homework, it's graded, but almost very few points. It's just basically encourage you to go do it. And I only do that just because back in the day, I had people just try to, and everyone looks at this material differently, believe it or not. Some people look at this and they're like, I had a lot of this undergrad, it's no big deal. And then they take the test and then, okay, well, there were some misunderstandings. So I just want to make sure people at least do the minimum number of problems. The homework is actually drawn from those test problems that I gave you. It's literally just like a subset of those problems, but then there's a whole lot more. So if you want to do the maximum, then work through the whole thing, but that's on you. And even for the ones I'm saying you must do, it just means you have to do a serious attempt on the problem. I'm not going to grade it carefully. I'm just going to say, oh yeah, they did it. Okay, good. You get the points. Okay.
Professor, under the homework one assignment, it looks like you may have attached the wrong folder. It says lab 0.
Oh, you're kidding me. Let me check.
It's also possible that it's just one, but no, it's like it's the actual lab 0.
Don't know how I could possibly have done that, but I'm very talented that way. Let's see. Sources. Oh, it's homework, the homework you said. So the assignments. Assignments. Homework one. Sure enough. Okay. Let's fix that. But I don't have to take time for that. So remind me if that doesn't fix by tomorrow. Get on me. Again, it's no rush. There is a due date assigned here. I just kind of pulled it out of the air. We'll shift it if we need to shift it. Okay. We will want to take time and do those problems in class. We will want to have a day where if you do choose to look at the old tests, you can come in and say, this problem or that problem is really hard. Let's do that one on the board and we'll do it on the board together. So all that for sure is going to happen before we do a day when you sit down and do a test. Okay. All right. Let's move. Okay, so we just had finished uniforms cost search. Before that, we did breadth first search. Okay, of the two, which looks the best, worst case? Assuming you're going to face hard problems, which would you choose?
Breath. Breath.
Breadth first. Why?
Because its complexities are better in the worst case.
Right, right. It's D to the D. D is always less than M, right? M is the deepest possible node in the entire tree. Okay? D is the shallowest solution node, always less. Okay, and it's exponential for crying out loud. We're playing with the exponent of a thing, right? It's just little tweaks to that are going to cause massive increase. Okay, so yeah, like I expressed at the end of the hour, this is kind of disappointing because I don't think this is a crazy algorithm, and I've actually seen it in use in some rare instances. Okay, it is pretty rare. Again, in the real world, not everything is worst case. And it was used because people actually tested and they're like, well, for my problems, this is actually very good. Okay. But a little bit of thinking helped me to come to grips with why worst case, it's really terrible. And so like this is like an actual problem I can describe for you. It's nothing like weird and out there, some really strange worst case like we generate in class, right? To do our mathematical arguments, we generate strange worst cases. If you imagine just the problem as simple as this, that we're going to do path planning, but our paths are just going to be multi-hop flights, single hop or multi-hop flights. Okay, we want to start at one city, we want to get to another destination city, and we want the minimum, let's say the minimum distance, air miles or minimum cost probably wouldn't be all that much different. But let's say it's distance. That's what I was assuming for this. Okay, and every operator for this problem is just to add another leg onto the flight. Okay, if we do uniform cost search. What was that number again? I was putting numbers on there. What does that number indicate?
You mean the cost?
These numbers. What are those numbers?
So the cost of that node.
Right. Is it the cost of the final solution going through this node or what?
It's the cost of processing.
No. It's the actual cost, solution cost, right? Which is it's not a computation or memory thing. This is a cost in terms of how bad or good is my path from point A to point B? How bad or good is my solution to the 8 puzzle? Okay. And it is not the solution cost. It's just the incremental cost so far. Okay. Right. So this example helps me to realize that, okay, yeah, even for some average problems, you can understand it could be a problem. So let me ask you, you can imagine I can generate all kinds of multi-hop flights here, that may or may not end in London where I want to go. I want to start in New York. I want to end in London. Which would be first to be searched out of all those paths? New York to LA or New York to London directly?
I assume New York to LA.
Why?
My assumption is that it is shorter to go.
Yeah, by about 1,000 miles. Yep. So yeah, so going to LA. Oh, okay. So that doesn't seem great. Okay, which would be first to be searched? New York to London or New York to Cleveland to Detroit to Chicago to Atlanta to Miami?
That.
Yeah. Yeah. And you think about how many of those bizarre paths there are going to be. And it's going to search all of those first before considering what's obvious to a person. So there you go. So I think the heuristic uniform cost uses, look for cheap solutions first is, there are domains where that's very sensible. But if you start thinking worst case, I think it's pretty obvious it could be bad.
In a case like this,
Yeah.
if you don't set a maximum depth for the search to stop at, could it just go infinitely? If there's like loops in your
it possibly could. I mean, well, think about it. There's only finitely many airports in the world, so actually no, it can't go infinitely, but boy, it can go deep. It could hit every airport, right? As soon as it hits one the second time, it's going to say no, circular. Okay. Other questions? Any questions about this? All right. All right. So I had some hope for the uniform cost search. I understand now, worst case, it's really kind of bad. All right, so let's look at something now completely different. This is like the polar opposite of breadth first search. It's depth first search. Okay, and the rule for adding in nodes here is now, this is the impolite search. This is the, yeah, I see there's a line at the checkout, but I'm here now. So I'll just go and, excuse me, I need to check out now. I'm important. That's kind of that model, okay? The new nodes that get added bump to the front of the list. Okay, now this makes for a very different pattern in terms of how you end up traversing this search tree over here. Okay, basically we search the children of the current node first, right? So we started with this node. I don't know why I go right to left, but I did. Okay, so we started with this one, so fine. So his children bump to the front, so they get explored first, and so on the whole way down. So you see, instead of going like peeling the layers of the onion, that's breadth first search. Now we've got deep dive, go as deep as you possibly can. If it's in infinite depth, there are infinite depth problems. If it's one of those, you better watch out that you're not going down an infinite rabbit hole there, or you're never going to get to a solution at all. Okay? All right. Now, that's clear enough. Is it obvious at this point? Hopefully it's pretty obvious that I'm doing the right thing and actually following the algorithm, right? Draw the first node, put the children on, they go to the front. Draw the next node, put the children on, they go to the front. You go, yeah, you got to check for circularity. You got to check for goals. You got to do those other things. But hopefully you look at this and say, yeah, that's same algorithm, just different rule for where you put the children.
Professor, you might come into the next one or so, but if we just said that this was only a depth 4 problem for the purposes of having it depicted on the bottom there. So we go down, we check green, it's not it. Does it go back up to the top, or does it
We go to
check the next off purple? So we go to red next.
That
That was the actual bottom of the problem.
okay. All right. Now we can answer that by just continuing to simulate the algorithm. So thank you. So, okay. So I see this is still kind of new for you guys. So fair enough. Let's start from here and let's see what happens. Right? If green has no children, that's kind of the case you're talking about. Right? Green would come off next. We goal test it, not a goal node. Now cross it out. No children. We just decided there are no children. So there's nothing to go to back to the front. So now we've got this. Okay, next node off is going to be red. Next node off is going to be yellow. Presumably it has some children. We process them. You see how it goes?
Yep, thank you.
Okay, now I want to flesh out the picture. That's important. It's important that you kind of see the pattern here. Any other questions about this? All right. Okay, so is this an optimal algorithm? Are we going to get the sheep solution first? No, and even like for the 8 puzzle, we could end up with like the worst solution first easily with this algorithm. So unfortunately, still not an optimal algorithm. Okay, computations. What's computations again? What are we supposed to be thinking about?
How many nodes we can have to process?
How many nodes we have to process? Worst case. We're going to build the problem. Absolute worst case. Now, where would you want to put the solution?
If they working, down right to left, which I understand would not always be the case, but
Yeah.
you would put on the bottom all the way to the left.
Bottom left. I absolutely agree with that. In which case, how many nodes from the tree are we going to search before we hit that
It would be the
solution?
same as to
B to the M. We're search all of them, and when you do the math, it's going to be B to the M. So unfortunately, another B to the M. Not very happy about that. Okay, how about memory? What's the worst case here? When is the processing list going to be the most full that it ever is? Does anyone have an intuition about that?
Yeah. When it gets to the bottom for the first time, would that be?
That's what I think. All right, well, let's think about it. What's going to happen? You're going to get the other B-1 children are going to be on the processing list. The other B-1 of this ones are going to be on the processing list, and so forth the whole way down. Okay, so we're going to have a picture like this. Right? The first dive, when you go all that, these nodes aren't on the processing list anymore. Okay, but all of these are. Okay, and when we go and do the next dive down, it's not going to be as bad because it's going to be almost as bad, but there are going to be a few less nodes there to deal with. Okay, so how many nodes are there going to be here? Right, these are B. So how many of these are on the processing list? B-1. Okay, and how many of these B-1s cohorts are on the processing list?
Um,
Yeah, M the whole way down to maximum depth. Okay. And so our complexity,
Yeah, no.
B times M. Okay. Now that is worlds away from B raised to the M and worlds away in the good way from B raised to the D. So anything that's exponential. Okay. Okay, so that is a little bit promising. This here. This I hate. Well, we haven't seen anything. I've yet to show you something that's optimal. Stay tuned. We'll get there eventually. All right. Okay. Questions about this? All right. As you see, we're moving kind of quickly, but all right, let's see. Okay, that's interesting. B times M. Let's see if we can make some hay out of that. Now you gotta be a little bit patient with me because I got this algorithm here that probably won't make much sense to you at first, but I'm going to actually use it to go somewhere else. Okay. So the idea with this is depth limited search. So it's depth first search, but where we decide a priori before we do any exploration, we say, yeah, I'm going no deeper than L layers. That's it. When I get to L, that's kind of the model that Andy was saying. Get there, whether they're children or not, I'm not looking at it. Okay. Okay, so that's kind of what you see portrayed here. Theoretically, I don't know, you get much sense of the depth limitation there. Oh yeah, see, the children of the purple node are not added because we took L to be 2, right? Layer 0, layer 1, layer 2. Children of purple would be layer 3. Not going to consider them. Are we good? Okay. Good. So it's depth first search, but no nodes deeper than L. Okay. Is this going to be an optimal algorithm?
No.
Okay. Not only is it not optimal, but if little d is greater than big L, and there's nothing to say that it isn't, we're going to get nothing. We're just going to straight up fail. Okay. All right. What about the computation complexity?
Wouldn't this just be the exact same as the one we just did? But
Okay.
wherever there was an M, you put an L.
Yes. Yes, that's exactly right. Okay. Because we've basically taken the tree we had that was depth M, and we've artificially said, no, just cut. We're going to cut at L. We're just going to make a cut. But otherwise, the algorithm performs the same. Does everyone follow that? That's very good, but fast, maybe for some people. Any questions? So this would then be B raised to the L, and this would be B times L. Okay, well, not very exciting given what we just kind of saw something very similar. Okay, but this is actually can let us do something that's quite interesting. This is another algorithm. Sorry, no animation here because the way this algorithm works is it actually runs the one we just talked about multiple times. This is called iterative deepening search. Okay, and it's kind of a big deal. Okay, so iterative deepening, what we're going to do is we're going to do a sequence of depth limited searches until we find a goal node, of course. Then we'll stop. But we'll start with L equals 0. I just look at the goal node. Then we'll do an L equals 1 search. Then L equals 2, and so forth. Is it clear to everybody what's done here? Okay. All right, now let me ask you, is this going to be an optimal algorithm?
I think it is.
Same mistake you made before. Yeah. Okay.
If depth is the cost.
Yes.
It is not.
Yes. Okay, what this will actually give you is the shallowest solution, right? Very much, because think about it, it's in a way that seems like kind of weird and inefficient, it actually is kind of peeling the onion like a breadth first search, right?
That's what I was about to ask you.
Yeah.
Could you distinguish this for us from a breadth?
Well, I will distinguish it for you. Look at all the computation that's being wasted here. Like, what's a depth 3 search as compared to a depth 2 search? It's like all the same computation, except it just goes one more layer down. All that redundancy is part of this algorithm. Okay. So that having been said, what's the computation complexity, right? Well, you can add it all up, right? I'm not going to actually, this is the one I'm going to kind of punt on the actual proof, but it's doable. It's doable.
Like a factorial type thing, because you're doing each search again.
Well, let's take a look. Great question. Let's take a look. Okay, so I ask, computations are B to the D. Why is this correct? The memory complexity is B times D. Can you see that? Right again, the fullest thing, yeah. So the fullest that the processing list can be is the fullest it can be across all these searches, and we're going to stop when L equals D, right? So it would be B times 0 would be the first number, B times 1, B times 2, B times 3, all the way down to B times D. That would be the fullest. I'm just talking about the record, the most full it ever gets for any one of these runs. Okay, and then we stop. So it's B times D. That may take a little thought, but it's not that complicated. Okay, it's again, keep in mind it doesn't matter that we're doing a whole lot more with the processing list. That doesn't matter. What matters is just what is the longest it has to be, because that's what determines how big, how much memory we have to have in our machine to do the computation.
The memory makes that little curious about.
Yeah, me too.
Like that.
Me too. Maybe I should actually prove it. Okay, but let's compare. If we do a normal depth limited search, just like 1 down to depth D, right? This would be the number of nodes that we would, worst case, have to process, right? That's basically the number of nodes in the entire tree down to depth D. I'm assuming we put the solution in the worst place for the algorithm, so it has to explore every node. Looks like this. Okay, well, now if we're doing iterative deepening, we do not only that, but all of these other searches with lesser L's as well. So you can kind of put them in a big triangle like this and add them up. Okay? And this is what you get. Okay? Okay, B to the D at the very end times 1. Okay? D plus 1 plus D times B plus D minus 1 times B squared. Okay, and what I'm going to ask you to believe here, based on a numeric computation, I should maybe just prove it, but I'm sure it's not all that hard. In fact, this sum ends up dominated by the last term. So what happens is, okay, if you do it numerically, again, using those B equals 10 and D equals 5 just to do a numeric experiment. If you just do the one depth first search, right? Don't bother with all that redundancy. You get this many nodes. And if you have all that redundancy added in, look, it adds up to just 10% more. Right? That is because of the way these numbers behave, because it's blowing up so fast. It's always the last number, which is the important piece. Now, this could be proven mathematically, but I thought there was enough math in this course. I left this out. Okay? Does it seem more credible now, Nick, when you actually look at this? Okay, so it's credible at least. Okay. All right. What else do I want to say here? Okay, let me just loop back. So let's just summarize. Nothing's optimal so far, so that's not really a discriminator. The computations, is this good?
That's not great.
It's exponential, so it's not great. Is there something better?
It's better than B to the M.
Yeah, better than B to the M. It's as good as we've seen.
Yeah.
We could say that. It's as good as we've seen. How about the memory complexity? Yeah, best we've seen.
Actually, that's
Yeah,
better.
yeah, better than B times M. Okay, so now you maybe see why this is a really important concept. All right. Now, what I want to do is talk about some extensions here. So this is one that's actually very important for simulation, but I didn't want to put it in this course, so I talk about it in the summer. And it's a way of trading memory for time is one way to think about it. It's going to cost you memory, but you will speed up the search. And the reason I didn't want to put this into this course, because it's yet more math to really understand why what I'm going to say is true. Well, we will talk about that math in the summer. Okay. Yeah, this optimization has a cute name called the closed list. So it's basically if you're path searching across nodes in a graph, you're basically at some point going to say this node is now closed. Any other solution that wants to go through this node, not going to consider it anymore. And you keep adding to that list. When something goes on the closed list, it never comes off. So it becomes essentially like you keep shrinking the search the search space. Okay, so yeah, so if you consider something like again, it's for summer to say why you can get away with this, but if you look at like a very degenerate case like this, where there's two ways to go from A to B, but they're the same. You know, there's two paths, one goes left, one goes right, but they're the same distance. Same from B to C and on down. When you actually search this, you're gonna, you know, the algorithm's gonna want to search all those permutations. Okay, and if this goes down from A through Z, there's going to be a lot of those permutations. Okay, and it's all kind of pointless because every path ends up being the same. It turns out in some very special situations, the first time you get to a search node, in this case B, is as good as any other time you're going to get to B. The first is at least as good. And so therefore, once I get to B via some path, I don't need to consider a second way to get to B. Right? I can just put B on my closed list and say, I'm done with B. Don't bother me with any more details about how to get to B, and so on. And so this can shrink in this case, in this really degenerate case, this would shrink what would ordinarily be a big search tree, an exponentially sized search tree. It'll shrink it down to just one pass down, and we're done. We won't consider anything else. Again, the big question is, yeah, when are you actually entitled to? That sounds great, right? When are you actually entitled to do that? That's the tricky bit. But for a lot of things in DoD modeling and simulation space, and in particular, shortest paths, quickest paths, you are very typically allowed to use this optimization. And other cases as well. Full story to some. Now, again, it's not for free, because what you got to do is, if I tell you that B is on the closed list, that means, oh, I've got to have a list, okay, of the closed items. Okay, and they could be, that list might eventually have, again, worst case, can have every node in my search graph in that list. So it may take me B to the M memory to construct that list. So we don't love this. This is horrible, but the speed up is super dramatic. And if you and this is really as much as anything what makes modern path planning search work the way it does. It's almost instantaneous in most applications, even on not very powerful computers, because we can optimize this. Okay, more details later. Okay, second extension I want to talk about is partial knowledge. So I started off saying, well, environments can be easy or hard, and there's different things that make them easy or hard. And then the next thing I said is, okay, we're going to assume the environments are as easy as possible for this first unit. Okay, so that's not great. Okay, and in particular, it's not great because partial knowledge is the norm for a battlefield simulation. Okay, including things even for path planning. You know, you may not know if the bridge is blown or not. Right? So how are you supposed to plan? Okay, so right, so there's various reasons why you can be in a partial knowledge state. It could be you just can't see everything. You don't know the initial state. It could be that there are some, maybe you know the initial state of the game. You know the bridge was there before the war, but there are stuff has happened that may be random, may not be, actions that might destroy a bridge, etc. Okay, so how can we deal with that? So there's no silver bullet for dealing with that. Those kinds of problems are genuinely harder, so that's why we didn't try to tackle it up front. But I'll just give you some notion that there actually maybe some hope, at least in certain cases, of using some basic probability theory, which are very basic, which you all know, to help us deal with this kind of a situation. Okay, but we do need to change the game here. Okay. So in a partially observed environment, we never know what state we're in, right? We never know what state we're in. So in other words, if we're playing the 8 puzzle, but I call the actions and you see the puzzle. Now it's not observed to me. Okay. And if I do something like say, move the blank down, you're like, okay, move the blank down. Okay, well, what do I know? Very little, but I know it's not, the blank isn't in the top row anymore. It's not that there's nothing that I know, it's just I don't know very much. Okay, so what you end up doing is where you used to just have one state, this is the state I'm in. Now you have to talk about, well, this is the possibility set. This is the set of possible states that I'm in, given what I know. Okay, that's the model. So your successor function, instead of returning all the children of one state, it has to return all the children of any state that's in your possibility set. Okay, and furthermore, if you really are determined to absolutely get to a goal, you must get to the goal. Then the goal is also going to be a set such that every member in that set is a goal state. Okay, if there's even one, if you say, what's the current possibility set? And I'm like, well, I could be in this state, that state, that. Are they all goal states? Well, they all are. Oh, except for that one there. Then am I sure I'm at a goal? I am not sure because I could be at that bad one. Seems like I'm probably not, but I could be. All right. So this is a trick as to do it. If you do it literally the way I do it on the slide, it will only work when these sets are rather small, but I still think it's instructive. So let's push it a little further. You remember this little 2-room vacuum bot? Okay. This problem is so small, we can use this technique very effectively. Okay. So let's consider. So this is actually a problem. This is actually a problem that you can solve with no sensors whatsoever. If with completely blind, you can solve this problem. Let's see if I can convey that to you. So let's say if this is the initial state, right? So we're starting up the vacuum bot, and I want to know, like, what's going on? Where's the vacuum bot? Where's the dirt? And you say, you don't get to know any of that. You're completely blind. Okay, then what state am I in? It could be any one of the 8 states. Okay? But when I say, all right, go right, attempt to go right, then, okay, I know that look at these 2 states up here. Okay, if I'm already on the right, then he's going to bump the wall and stay where he is. If he was on the left, then he's going to move to the right. Okay, so what's our 2 states over here end up getting condensed into 1 state over here. So without actually sensing anything, and only by taking actions, I'm getting smarter about the state. Now, this is a known phenomenon in warfare, and it has a term I'm just exceptionally fond of because I always thought it was so cute. Reconnaissance by fire. Reconnaissance by fire is like, is there a guy behind that rock? Well, I don't know. Here's the hand grenade. Boom! There's no guy behind the rock. Okay? But I didn't get smarter by seeing. I got smarter by taking an action. Okay? That's the idea. So if you look here, you see that if I go right, now let's see, here would be, let's say the left is my home. So this would be my goal state. If I go right and then suck, and then left, and then suck, I'm at a goal state, 100% sure, even though I never got any sensing. Okay, this is an extreme example, right? It's extreme, but gives you an idea of some possibilities here. Okay, now you can do even better than this by using probability. I didn't use it here, but usually, even when we're blind, we have some kind of prior probabilities of what's going on. So if this is my set of current bag of possible states, and now I have an expert, or I have some old intel, or I have something to base some analysis on, and I might know that, well, it's very unlikely, 0.05 probability for each one of these states that I'm in this state, 10% probability I'm in one of these, 25% in one of these, add it all up, 25 plus 25, that's 50, 60, 70, 80, 90, 95, 100, 100%. It's a legit probability distribution. Okay. And then it is very easy when I say, oh, I want to go right, then you can just say, oh, well, what's going to happen? Well, these 2 states, 5% states, turn into this state. So what's the probability of this state? 10%, because both parts of the probability space come together. It's now 10%. These become 20% states and this becomes a 50% state. There's very little computation involved with that. And now you can do more sophisticated stuff. Like now if you say, you must achieve the goal, you absolutely have to achieve the goal. Well, if you 95%, you can achieve the goal with 95% probability, that's good enough. Oh, okay. Now I don't have to, in general, not for this problem, but in general, I don't have to take as many actions and I'll be able to more quickly say, okay, this mostly goal states in my possibility set, add up the probabilities, and I've done what I was asked to do. Okay, any questions about that? Hopefully that makes some sense. All right. All right, so a couple more extensions, but both of them based on this idea. Reverse direction search. So this is the thing, a search is probably pretty new for most of you, okay? So what I want to point out here is that search is not a symmetrical type of a beast. Okay, so like look at this example, look at this search tree here laid on its side, right? Your initial state, final state, right? If we're going to search starting from the initial state, I'm probably going to have to do some searching to get to the solution. But if I know the solution, right? Again, you need to know the solution, right? So this doesn't work for 8 queens because we didn't know how to do 8 queens, but it works for the 8 puzzle. We know the solution. We can just as well think backwards, right? If I were at the solution, what actions would I need to take to get back to the current state of the world, right? In fact, we do this kind of thinking all the time as people. And we understand sometimes it works, sometimes it's a real loser, right? But for a case like this, looks good, right? How could I have gotten to this state? Well, only from this one. How could I get from this? Only so there's no search going in the reverse direction, but in the forward direction, you have to do work. Good. Okay, so, but again, you got to be able to invert the successor function, and you've got to know what your goal state actually is to take that as your now pseudo initial state and search back in the opposite direction. Okay. All right. All right. So last thing for today, what we can do is we can take a normal forward directional search and combine it, interleave it with a reverse direction search. So the concept's going to be, we're going to kind of search from both ends and hope to meet in the middle. Okay? So obviously you've got to meet all the conditions for reverse search. You've got to know the goal state. You've got to be able to invert the successor function to be able to ask of a state, well, what parents could you have come from, or what parent could you come from? Okay. Now, if the max branching in the reverse direction is also B, just to make it easy. If it's different, we could redo the analysis, but let's just say it's B in both directions. So every child could have maybe come from 10 parents. Every parent has 10 children, right? B is 10. Okay. Then you can achieve a time and space complexity of B to the D over 2. Now that's absolutely the best we've seen. Now let's think about how you could do that. What if you do breadth first search in both directions? Right? What's the computation complexity of each search? Again, assuming you're going to meet in the middle, right? So that would be depth D over 2, or we know those are both B to the D for computation and memory for breadth first search. So it's B to D. Now it's 2 times B to the D over 2. Well, that's just big O B to the D over 2. Okay? So that is amazing. Now, there also is an additional cost with this, additional conditions to meet, and then also you're going to need to keep track of all the nodes that are on the fringe of each one of your search trees to know. Otherwise, it's going to be like ships passing in the night. The reverse direction search is just going to move right by the forward search, and you're not going to get the beautiful B to the D over 2 result. Any questions about this? Pretty cool, right? Think about it. Think about it. Some concerned looks. Well, that's only natural, but think about it. If you don't have questions, just think about it. All right, so I kind of wrap things up here into a big table, which I guess we'll use this for our starting point when we reconvene tomorrow at 1400. Just summarizing what we've said so far, maybe we'll just use that as a jump off point tomorrow. Okay? All right. Yeah, feel free to look at the homework if it pleases you. I don't, I'm not actually sure what searches are on the homework, but there probably is a breadth first search or whatever. You can start to see what kind of things. Certainly you can look, if you look at the tests, there's all kinds of different search type things in there. Again, if you just want something to do now as opposed to in a few days from now, depending on your schedule. Okay, think about when we want to do the test, in particular, try to, if you know there's going to be some known bad days to avoid, if you could bring that to class tomorrow, that would be awesome. If you're able to. Okay, all right. See you tomorrow.